On November 12, 1993, at a hotel in California, a dispatcher at an elevator repair company tried to page one of his technicians. No response. He tried again an hour later. Still nothing. He sent another technician to find him. The second technician arrived at the hotel, met the chief engineer, and together they searched the building. They found the man inside the elevator shaft, lying across the counterweights of car number 1, pinned between two steel spreader beams. While he had been leaning forward over his work, the counterweight from the adjacent elevator descended silently and struck him in the back of the head. The coroner's report listed the cause of death as multiple traumatic injuries. He had been alone. Nobody heard or saw it happen. The counterweight just came down. This is the machine that nobody thinks about. A block of iron or concrete weighing thousands of pounds, traveling up and down inside the walls of buildings all over the world, every second of every day. And when it meets a human body in its path, it just keeps going, because that is the only thing a counterweight knows how to do. An elevator counterweight is a simple idea with brutal physics. In a traction elevator, the kind that uses cables and a motor rather than hydraulic fluid, the car hangs from one side of a set of steel cables. The counterweight hangs from the other side. When the car goes up, the counterweight comes down. When the car goes down, the counterweight goes up. The counterweight typically equals the weight of the empty car plus about 40 to 50% of its maximum passenger load. For a standard commercial elevator rated at 4,000 pounds, that puts the counterweight at roughly 5,000 pounds. That can mean 2.5 tons of cast iron blocks, stacked in a steel frame and riding on guide rails inside the elevator shaft, silently traveling in the opposite direction from the car, whether the car is above you or below you. The purpose is energy efficiency. Without a counterweight, the motor would have to lift the full weight of the car and its passengers on every trip. That would require enormous power and put tremendous strain on the cables. With a counterweight balancing the load, the motor only has to overcome the difference between the two sides. When the car is at about 40% capacity, the system is perfectly balanced, and the motor barely works at all. It is an elegant engineering solution. It has been standard in traction elevators since the technology was developed in the mid-1800s. Elisha Otis demonstrated his safety elevator in 1854. By the 1880s, electric traction elevators with counterweights were being installed in commercial buildings across American cities. And from the very beginning, the counterweight started killing people. If you want to see which machine I cover next, subscribe and drop it in the comments. Now here is why the counterweight is different from the elevator car itself. The car has doors, lights, buttons, bells, and a floor indicator. People see the car. They think about it. They worry about it falling, about the cables snapping, about getting stuck between floors. The counterweight gets none of this attention. It lives in the shaft, behind walls, out of sight. Most people who ride elevators every day of their lives have never seen a counterweight and do not know one exists. But it is always there, always moving, always occupying space inside the shaft that a human being could also occupy. And unlike the car, the counterweight has no doors to keep people out of its path, no sensors to detect an obstruction, no emergency brake triggered by the presence of a person. It rides its guide rails from the top of the shaft to the bottom and back again, and whatever is between the counterweight and the wall gets compressed into whatever space remains. Could you imagine working inside a dark shaft with 5,000 pounds of iron sliding past you in silence? If you can, let me know in the comments. The people who die from counterweights are almost exclusively the people who work on elevators, maintenance technicians, mechanics, installers, and construction workers. They are the people who enter the shaft to do the work that keeps the system running. According to a report from the Center to Protect Workers' Rights, elevator and escalator incidents kill approximately 30 people and seriously injure about 17,000 people per year in the United States. Almost half of the annual deaths involve workers who were installing, repairing, or maintaining the equipment. Among those worker deaths, 16% were caused by being struck by the elevator car or counterweight, and 18% were caused by being caught between moving parts of the elevator system, including the counterweight, the car, the shaft walls, and the guide rails. Here is what makes the counterweight so dangerous for the people who work inside elevator shafts. The shaft is not a large space. In many buildings, the clearance between the counterweight and the shaft wall is measured in inches. The counterweight travels on its own set of guide rails, usually on the side or rear of the shaft, depending on the building's configuration. When a technician enters the shaft to work on components like the governor, the cables, the door mechanisms, or the car frame, they often position themselves in areas where the counterweight can pass. If the elevator is called to another floor while the technician is inside the shaft, the counterweight moves. In older buildings, there may be no lockout system to prevent the car from being activated while maintenance is underway. In newer buildings, lockout procedures exist but are not always followed. The result is the same. A mass of iron descends or ascends through a narrow space occupied by a human being who did not hear it coming. In 2007, at the City Center construction project in Las Vegas, a 65-year-old operating engineer named Harvey Englander was struck and killed by the counterweight of a man lift. OSHA investigated and found 6 safety violations. After a conference between the agency and the construction company, the findings were withdrawn. In the same project, 2 carpenters were crushed inside an elevator shaft by structures weighing 7,300 pounds. OSHA fined the contractor $14,000. After another conference, the fine was reduced to $7,000. $7,000 for 2 lives. That pattern repeated across the country for decades. A technician enters a shaft. The elevator activates. The counterweight descends. The technician is pinned, crushed, or struck. An investigation finds violations. A fine is issued. The fine is reduced. The work continues. But it was not just modern elevator shafts where counterweights killed. In the late 1800s and the early 1900s, freight elevators in factories and warehouses were far more dangerous than any passenger elevator in a hotel. These were open platform lifts, often without enclosed shafts, without gates, without any barrier between the workers loading cargo and the moving machinery. The counterweights on these elevators traveled through open hoistways alongside the platforms. Workers loading and unloading freight stood feet away from multi-ton weights that moved every time the platform was called to another floor. Common injuries included being struck by passing counterweights, being crushed between the counterweight and the shaft wall, and being caught between the descending counterweight and structural beams. In many factories, the freight elevator shaft was simply a hole cut through the floors with a wooden railing around it. The counterweight ran up and down the side of this hole with nothing separating it from the workers on each landing. The Cook County Coroner's Office in Chicago compiled 401 elevator accident reports from this period. The descriptions used the same words over and over: crushed, caught, squeezed, struck. The accidents involving counterweights shared a common feature. The victim almost never saw it coming. The counterweight approached from above or below, in a blind spot, in a dark shaft, behind a wall, while the victim's attention was on the elevator car, on the load, or on the work in front of them. The counterweight is the thing behind the thing you are watching, and that is exactly what makes it lethal. You are probably wondering whether the design ever changed to make this safer. The answer is yes, but slowly and incompletely. Modern elevator codes require screens or barriers between adjacent hoistways to prevent workers from being struck by neighboring counterweights. Lockout and tagout procedures are supposed to ensure that elevators cannot be activated while technicians are inside the shaft. Speed governors regulate the velocity of both the car and the counterweight to prevent runaway conditions. Safety gears can grip the guide rails and stop the counterweight if the cables fall. In many new installations, sensors and interlocks make it significantly harder for someone to enter the shaft while the system is active. But the fundamental design has not changed. The counterweight still rides inside the shaft, still moves in the opposite direction of the car, still weighs thousands of pounds, and still occupies space that a person might also occupy. When a lockout is skipped, when a sensor fails, when a technician takes a shortcut, or when someone calls the elevator while a worker is inside the shaft, the physics are identical to what they were in 1890. A mass of iron moves through a narrow space, and whatever is in its path gets compressed. From January 2020 to September 2023, 41 workers were killed and 21 were injured while repairing or working near elevators in the United States. More than half died from falls into the shaft. But counterweight deaths, though fewer in raw numbers, are among the most disturbing in the industry because of how they happen. There is no warning, no Schutzbund, and no time to react. The technician is working, the counterweight descends, and then the technician is not working anymore. The counterweight is the part of the elevator that riders never think about, that building managers rarely inspect, and that technicians respect more than anything else in the shaft. It has no moving parts of its own. It is just weight, iron blocks in a frame, sliding on rails, going where the cable takes it. The most primitive component in the most common machine in the modern built environment. And after more than 150 years of elevator engineering, it still kills people the same way it always has. Silently, in the dark, behind the wall. Thanks for tuning in. For more stories about the machines and structures that killed the people who worked inside them, check the videos on screen. If you want to see what we investigate next, subscribe.